So, in our earlier lecture we discussed about the similarity rules for linearized 2D subsonic and supersonic flows, and where we had an arbitrary A, and for various choices of A we got different rules, and in particular we choose 4 different values of A and obtain 4 different similarity rules, which are that C p is function of tau by root over 1 minus m infinity square, and as we mentioned that this is valid for both subsonic and supersonic flow if we make this term sign independent. And for another choice of A we obtained tau, and for another case we had tau function of root over 1 minus m infinity square, and all these as we mentioned that they are called Prandtl-Galois rules. We also had a Gosset rule which gives C p as 1 by 1 minus m infinity square function of tau root over 1 minus m infinity square, which is called the Gosset rule. Now, let us see what these rules in particular say. Let us consider this first rule, that is this particular. This simply says that the pressure coefficient on an airfoil or a 2 dimensional geometry in subsonic and supersonic flow is function of tau by root over square 1 minus m infinity square absolute. It simply says that if this parameter, that is tau divided by square root of absolute 1 minus m infinity square, is invariant, then C p also remain invariant. That is, for airfoil, if we consider airfoil of same family, if the thickness varies in such a way that T by 1 minus m infinity square is constant, then the pressure distribution on the airfoils will remain constant. Meaning, let us consider a subsonic flow. We know in subsonic flows with increasing m infinity, this says that thickness will increase as proportional to 1 by root over 1 minus m infinity square, and this rule then says that as the Mach number, free stream Mach number increases in such a fashion that the thickness is also changed by this factor or by this multiple 1 by root over 1 minus m infinity square, then the pressure distribution will remain constant. And see that for a same family of airfoils, we can have pressure distribution over different thickness at different Mach number, if we know the pressure distribution on a particular thickness at a particular Mach number. So, see that is the utility of this first rule. The second rule clearly says for a given member of a particular family of shape, the pressure coefficient increases with m infinity as 1 minus m infinity square to the power minus half, or as 1 by root over 1 minus m infinity square. That is, if we have a fixed airfoil of a particular family, then as free stream Mach number increases, the pressure coefficient on that, or the pressure distribution on that airfoil increases by a multiple of 1 minus m infinity square to the power minus half. So, you see that if we have a particular airfoil, let us say a 4 digit symmetric section NACA 0012, we know its pressure coefficient at say an incompressible flow, which corresponds to Mach number 1. Then for the same airfoil at a different Mach number, the pressure coefficient is obtained simply multiplying that incompressible flow pressure coefficient by the factor 1 minus m infinity square to the power minus half. So, you see that this is also a utility of this form of the Prandtl-Glauert relation, that for same particular airfoil, if we know the pressure coefficient at an incompressible flow or at any low Mach number, we can get it at other Mach number simply by multiplying the pressure coefficient at any particular point with the factor 1 minus m infinity square to the power minus half. The third rule can be interpreted that the pressure distribution or the pressure coefficient at any point is proportional to the thickness if the Mach number remain fixed. So, for a fixed Mach number, the pressure coefficient at any point is simply proportional to the thickness. Finally, the Gosset rule, it says that C p increases with Mach numbers as 1 minus m infinity square to the power minus 1, if the thickness also increases with as 1 minus m infinity square to the power minus half. That is, the C p will increase as a multiple of 1 by 1 minus m infinity square if the thickness increases as a multiple of 1 minus m infinity square to the power minus half. That is, for a given shape or given family of shape, if the thickness increases by 1 minus m infinity square to the power minus half, then the pressure distribution on that same geometry will increase by a factor of 1 minus m infinity square to the power minus 1. As you will see later, that Gosset rule applies to axially symmetric flow as well. We must remember that these similarity rule, which are valid for linearized 2D subsonic and supersonic flows, become less accurate as we approach the transonic range or the hypersonic range, since in both the cases, that is in transonic flow as well as in hypersonic flow, the linearized form of the equation is not valid, and consequently the accuracy of the similarity rules, either the Prandtl-Glauert rules or Gosset rules, also diminishes as we approach one of these range. So, to get a reliable result, this rule must be applied for only those Mach numbers which are strictly in the subsonic or supersonic range. Let us now consider the 3-dimensional planar flows. Similarity rule for three D planar flows. Which are quite important because these are applicable for flow over wings. Let the 3-dimensional planar boundary let us say that let phi 1 x y z be solution of flow over a wing at free stream speed u1, which of course corresponds to Mach number m1. So, phi 1 x y z this satisfies. The governing equation, which can be written and also the appropriate flow tangency condition on the surface, which is now given as where C is chord and B is span. C is chord and B is span. And tau 1 is as before the thickness ratio. And then the boundary condition is or the linearized boundary condition the linearized boundary condition. Now, as before, let us consider a second function. Let us take a second function phi 2 xi eta zeta xi eta zeta such that as before we have phi 1 x y z equal to a into, as before, a into u 1 by u 2 phi 2 x y into root over 1 minus m 1 square by 1 minus m 2 square, and z is also that is, we are applying this transformation that xi equal to x eta equal to y into root over 1 minus m 1 square by 1 minus m 2 square, and z is zeta equal to z into root over 1 minus m 1 square by 1 minus m 2 square. Now, if we substitute this in the governing equation, so phi 2 substituted in the governing equation so that it satisfies that is, it satisfies a potential flow in the xi eta zeta system, a potential flow in the xi eta zeta space at free stream speed m 2. That So, phi 2 is satisfies the potential equation or the potential flow at M 2. Now, if we try to relate the boundary conditions, what we get is d phi 1 d z at z equal to 0 is same as a into u 1 by u 2 root over 1 minus m 1 square by 1 minus m 2 square d phi 2 d j at zeta equal to 0. Now, if we equate the boundary conditions, tau 1 d dx of function of x by c into y by b 1 equal to a into root over 1 minus m 1 square by 1 minus m 2 square into tau 2 d d xi f of xi by c and eta by b 2. Now, this equality will hold. This equality will hold if first of all f is same. So, to satisfy the equality, f must be same, which actually implies that the profile shape must be same. Must be similar. That is, the wing profile must be similar. The two wings must be of similar. We also have that tau 1 must be a into root over 1 minus m 1 square 1 minus m 2 square into tau 2, as well as y by b 1 equal to eta by b 2, which is y by b 2 root over 1 minus m 1 square by 1 minus m 2 square. Or b 2 or b 2 by b 1 equal to root over 1 minus m1 square by 1 minus m2 square. So, you see that the phi 2, the way we have chosen or the transformation that we have applied will satisfy another potential flow over a body which has same profile shape, whose thicknesses are related by this relation and whose span are related by this relation. So, you see that the flow are similar, that the solutions are similar if the geometry is of similar, the profile shape are similar, the two thickness of the two different planar body or the two wings relate by this relation, and the span of the two wings relate by this relation. Now, the pressure coefficient as before, we have C p 1 equal to A C p 2. And in this case also we have seen that the A remains arbitrary. It has not been possible to find a specific value for A. So, whatever choice we can have for A, the result will be same, and this is also follows from the same fact that the governing partial differential equation in this case is also homogeneous. So, any solution multiplied by a constant coefficient remains the solution. As far as the boundary condition is concerned, so A is arbitrary. So, once this is known, then we can have the similarity rule. So, the similarity rule is C p by A is a function of tau by A into 1 minus m infinity square into B into root over 1 minus m infinity square. Since B is proportional to aspect ratio, this can be written as and this is the aspect ratio of and combined law for subsonic and supersonic flows is C p by A as function of tau A absolute of 1 minus m infinity square as well as aspect ratio here also you can have different choices for A as before, and the resulting rules can be interpreted accordingly. However, we will be seeing that there are two parameters here, the thickness ratio as well as the aspect ratio, and both are to be adjusted accordingly. So, as one particular rule, the first rule of first Prandtl-Glauert rule in the earlier case, that C p remains invariant over the profile if tau by square root of 1 minus m infinity square remain invariant. Same rule applies here also, if tau by root over 1 minus m infinity square and aspect ratio into square root of 1 minus m infinity square, both the parameter remain constant. That is, as Mach number increases, if we increase the thickness following this and reduce the aspect ratio following this, then the pressure coefficient on the wing surface will remain constant. And once again you can see that knowing the pressure distribution for a wing at a particular Mach number can give us the pressure distribution at different Mach number or for a different thickness and different aspect ratio wing at the same Mach number. Let us now consider the similarity rule for transonic flow in two dimensional case. To the transonic flow, of course, linear potential flow, small disturbance potential flow. You may recall the governing equation we had d2 phi dx square plus 1 by 1 minus m infinity square d2 phi dy square is gamma plus 1 into m infinity square by 1 minus m infinity square into u by u1 u by u infinity, or let us say 1 by u infinity d phi dx d2 phi dx 2. We may recall that in deriving the small perturbation equation, we mentioned that when m infinity is close to 1, this coefficient of d2 phi dx 2 on this right hand side is comparable to the coefficient of d2 phi dx 2 on the left hand side, and consequently they are comparable, and are not negligible. This is true when m infinity is close to 1. Consequently, we see the equation is nonlinear here and closed form solution is not readily available. So, in this case this similarity rule will have much more usefulness than they are in case of subsonic and supersonic flow. Now, to derive the similarity rule we will follow the same steps, that is, first of all we will consider a particular solution of this flow over a chosen geometry, and then we will consider a second function related to this first flow solution, which is of the same form, and then see that what are the under what conditions that second function will be a solution of this governing equation. Once we obtain those conditions required, so that the chosen function is also a solution of this equation, we will try to frame the similarity rule. So, first of all we will consider a solution corresponding to free stream speed of u infinity or m infinity in a gas, since in this case the gas itself is also present in the equation. So, we have another additional option where we can change the gas also. So, first step, consider phi 1 x y is solution of the equation when free stream is given by m 1 u 1 in a gas with gamma 1. Since phi 1 is a solution for this equation corresponding to m infinity equal to m 1, u infinity equal to 1 and gamma equal to gamma 1, we will have that this phi 1 satisfies this equation, that d 2 phi 1 d x square plus sorry 1 minus m 1 square d 2 phi 1 d y square equal to gamma 1 plus 1 into m 1 square by 1 minus m 1 square into 1 by u 1 d phi 1 dx d 2 phi 2 dx square. Again introduce that phi 2 xi eta as before, that is x equal to xi and y root 1 minus m 1 square by 1 minus m 2 square equal to eta, and phi x y equal to a into u 1 by u 2 phi 2 xi eta sorry phi 1. Now, if we substitute this phi 2 in the governing equation. Substitute this phi 1 in the governing equation, and what we get that is we are substituting this expression for phi 1 in this particular equation, putting this phi 1 here. What we are getting is d 2 phi 2 d I square by 1 by 1 minus m 1 square d 2 phi 2 d eta square into gamma 1 plus 1 square by 1 minus m 1 square into a y 2 d phi 2 Now, if now see that the equation that phi 2 satisfies, it not exactly the equation for not exactly the governing equation corresponding to the free stream speed u 2. It is not exactly the small disturbance equation for transonic flow. Not exactly the small disturbance equation. However, if we want that phi 2 is a solution of the transonic small disturbance equation, so if phi 2 xi eta is to satisfy the equation in xi eta plane for a flow with free stream U2 M2 in a gas with gamma 2, then this coefficient on the right hand side, that must be equal to gamma 1 plus 1 into m 1 square by 1 minus m 1 square into A should be gamma 2 plus 1 into m 2 square by 1 minus m 2 square. So, if or A must be gamma 2 plus 1 by gamma 1 plus 1 into m 2 square by m 1 square into 1 minus m 1 square by 1 minus m 2 square. So, we see now that the A is no longer arbitrary. If we want this choice of our second function phi to xi eta is to be a valid potential function, then this A must be this. So, it is not arbitrary in this case. Or other way, that if we have a solution phi 1 for a transonic flow at m 1 and then we choose another function similar to this function phi 1 and we want it to be a solution at m 2, then the A is no longer arbitrary, as in case of a subsonic or supersonic flow, where the governing equation was linear. In this case, this A must have this specific value, so that the similar choice can also be a solution. If we consider the boundary conditions, as far as the boundary conditions are concerned, you see there is no change at all with the two dimensional subsonic or supersonic flow and this transonic flow. So, the boundary condition or the result that you obtain from the consideration of boundary condition will remain the same. So, you can say that consideration of flow tangency boundary condition will again give us that tau 1 equal to A into root over 1 minus m 1 square by 1 minus m 2 square into tau 2. Which happens to be the same relation, but the A is no longer arbitrary. Similarly, if we compare the pressure coefficient, remember we had C p 1 equal to A C p 2. Or other way, that two transonic flow will be similar and their pressure coefficient will be related by this relation if the two thicknesses are related by this relation and the coefficient A is given by the relation that we have obtained. So, in this case, that the two solutions are similar if A is the specific that we have obtained and the two thicknesses are related by this relation, and in such a situation the pressure coefficient will be related by this relation C p 1 equal to A C p 2. And so, the similarity rule gives C p by A before C p by A equal to function of tau by A root 1 minus m infinity square. And substituting for A, we have for C p we substitute gamma plus 1 m infinity square by 1 minus m infinity square is function of tau into gamma plus 1 m infinity square by 1 minus m infinity square to the power 3 by 2. So, this is what is the transonic similarity rule. This is the transonic similarity rule. Now, we define parameter chi, which as 1 minus m infinity square by gamma plus 1 into tau m infinity square to the power 2 by 3 and multiply both side by this. Then we have C p multiplied by gamma plus 1 m infinity square to the power 1 by 3 by tau to the power 2 by 3 equal to function of 1 minus m infinity square by tau into gamma plus 1 m infinity square to the power 2 by 3, that is a function of chi. So, this is what is treated as the final form of the transonic similarity rule, and what we can see is that This rule of course valid for the entire range of subsonic to supersonic flow. Rule is valid for entire subsonic to supersonic range. So, this particular rule is valid even for subsonic as well as supersonic flow. This is in contrast with that linearized rule, which is not valid for the transonic flow, but this transonic rule is also valid for subsonic and supersonic flow, which is quite easy to comprehend, because the subsonic and supersonic flow equations are just a special case of this particular equation, and the Prandtl-Gosset rules and Gosset rule, these are all special cases of transonic similarity rule. Now, we will see that how can we interpret this particular rule vis-a-vis the subsonic and supersonic rules in our next lecture. So, we have derived the similarity rule, but we will for transonic flow, which is the most useful similarity rule, and however, we will discuss about this rule in the next lecture.